after we talked about mostly mathematical topics that are not so directly connected to our main area of algorithms, I want to bring it back to the more computer sciencey part of proofs. And again, the purpose there is on one side showing you some really formal techniques that make such statements or the proofs very rigorous. Although we will not use them in all the full gory details, that's the kind of thinking that you should develop when you think about algorithms and argue why they are correct. So that's part of this last section. In this section, we'll discuss proof techniques or templates for showing the correctness of programs and what that even means in our case. This is a whole area called formal verification, which is really not the focus in this module. But a little glimpse of it is part of every algorithm design. When you design an algorithm for an algorithmic problem, you want to make sure that the algorithm is fast, but it's only useful if it's fast, if it's also doing the right thing. And so implicitly, we always want a correctness proof as well, at least informally. In formal verification, the correctness of a program is split into two parts. One is that the program terminates, so at least eventually it halts, it stops running, which is a far cry from being efficient. And we'll spend the rest of this module on efficient algorithms. But for this section, it doesn't matter how long it takes, as long as eventually it stops running. That's at least part of the game. And then when it stops running, our assumption is all algorithms are essentially boxes that take some input, and then they produce some output. I'm sure you have seen this box many times, but the implicit assumption among this, I mean, there's some computation going on inside of here. These are cogwheels, obviously, not sunny side up. There's some computation happening inside there, and it's supposed to produce an output. Well, it can usually only produce an output when it stops running, or you would have to define what that otherwise means. So the second part is about producing the correct output when it stops. Now we'll restrict it to a specific part of the program here, but it is actually more general than that. So you can use it on different parts of the program to generalize it. The general template, if you want to prove a program terminates, is something like a potential function argument that you may have seen. In this case, I'm assuming we have some recursive procedure, so a function that calls itself. Maybe if we take a step back, why would a program ever not terminate? Well, it only doesn't terminate if it somehow gets into an infinite loop of some sort. And that can either be a while loop, while something is not true, keep going. And if that never is true, then it is stuck in that loop forever. But it can also happen in a recursive function that keeps calling itself and never stops. In a way, these two are equivalent. If you've had some more theoretical computer science modules, you'll maybe even have proven that. You can translate one to the other and back. But these are the two main reasons why a program might never finish: infinite recursion or an infinite loop. And so for the proof here, we'll assume that there's a recursive function, some procedure proc that has a bunch of parameters, and it might call itself at several places in the body. So what we'll do is we'll define, to show that this eventually terminates, we'll define some function that takes the parameters of this procedure and converts them somehow into a number. And how exactly that works doesn't really matter so much. You'll have to pick a concrete example, and you will do in the tutorials next week, on how to make sense of how the parameters turn into a number. Abstractly speaking, the potential is some function that gives you a natural number back for every set of possible parameters for this function, for the procedure. And because it's a natural, so I'll use this n0 as the set of natural numbers, 0, 1, 2, and so on. And I'll try to use n without the 0 for the same thing, but starting at 1. If that's important, I might actually write with a subscript greater equal 1 to make it more clear. So this potential is at least 0 by definition. There's no smaller natural number. What we have to prove termination is whenever the function calls itself, the potential of these parameters that it calls itself with is smaller, strictly smaller than the potential of the parameters it was called itself. So in other words, at least the potential drops at least by 1. Again, because it's natural numbers, if it's strictly smaller, it has to be at least 1 smaller. And that's pretty much all for the abstract template. Again, you'll flesh out in an example how this works next week. But that means the procedure has to terminate because it has to start with some finite value, namely the potential of the initial parameters that it's called with. And whenever it calls itself, something strictly goes down. You can only do that a finite number of times in the integers. Then you flat out at 0 and you can't go further. A similar idea works for loops. If you have a while loop, then there will be some parameters, there's some variables. So it's not as explicit as in a function call, but you will still have variables that change their value over time. And so if the while loop eventually terminates, there must be some way to get a potential from the variables that always decreases. So it's kind of, it works in both ways. But the trick is to find the potential function. Depending on how complicated the code is, that's quite a formidable task. Again, I'll refer you to the tutorials for an example. What I'll show you in detail in the rest of today's session is for the second part, how do we prove the correctness of a piece of code? So let's assume we already established it does terminate. What does that even mean for the code to be correct? The way this is almost always formalized in the form of for logic is that you run a program. Maybe it's worth writing that down. You run a program assuming some conditions that are true. So for example, that your input is of a certain form. You don't accept arbitrary bit strings. You want certain structure. For example, you may have a function that takes a number and the number should be at least 1. I'm making this one up, but that could be a precondition. Then you run your code. So this could be conditions on the variables, on the input. Then you run a piece of code and you try to have a formal implication that the preconditions with the code imply a postcondition. Which again is some statement about the variables and the output. For most types of programs, this is relatively easy to do. If you just have an assignment of a variable, for example, then the precondition has something to say, and then the postcondition is there's a new variable and it has the value that you assigned it to. And similar for if statements, these are all relatively easy to handle. The only interesting part is when you have a while loop. Because then again, the same code might run many times, and it's not so clear what its effect is. So there's a template for handling that. You have some precondition before the loop, and you try to prove some postcondition after running the loop. And the template says that's not enough. You also have to come up with what's called a loop invariant. That's a specific statement, and it has to satisfy three conditions. Namely, it should be true before the loop, so I has to be true here. Then if you have the invariant and the condition that means you continue another iteration of the while loop, then the invariant has to be reestablished at the end of the loop. And finally, if you have the invariant after the loop, then together with the statement that the while loop does not continue must give you the post condition you wanted. Okay? Let's see a concrete example for this one, and maybe that becomes a bit clearer. The example is this piece of code. It's a simple function that computes the maximum entry in an array of numbers. I'm sure most of you would be give you 5 minutes and you coded this up in some language. So how would you find the maximum in an array of numbers? Well, you go through, you keep a running maximum from the beginning in this case. So we have a variable I that goes through the array from starting at 1 and until the end. So I should maybe point out my arrays start at 0. That's the default. And I use these square brackets to index elements like in almost all languages. And here this function has a precondition, namely that n is at least 1. You're not allowed to call the function with an empty array. I guess it makes sense because it's hard in general to return the maximal element of an empty set. It's not well defined. If it's numbers, maybe you can find some infinity value, but let's ignore that. So we have a precondition, which is this one in this case. That's something the program can rely on when you run it, and your proof can assume that. Then how do you find the maximum? You keep a current maximum that's starting with the first element, and then when you iterate through the array, if the new element is bigger, then that's the new running maximum, and otherwise you keep the old one, right? So the code is not very interesting or not very complicated, but how can we formally prove that this does the right thing? So clearly, the post condition should be the output, what I return here, current max at the end, should be the maximum element in this array. That's the post condition we want. And that's spelled out here in formulas. So at this point, at the line 13, or after line 13, I want the current maximum variable, current max, to be the largest element in the array. And well, I hope that's readable for you, even if you haven't seen that before. It just means let k run in this range and then pick the largest value that you get on the right. Okay, so how do we prove this? The tricky bit is to find a loop invariant. And I've already done that tricky step for you here. So I'll just show you how the final proof works. This will not really teach you how to find these proofs, but I mostly want you to be able to read them and understand and recognize if they're correct. Okay, the loop invariant is often something you don't find in the first round, but you have to refine, and that's the part I've already done for you. There are these two bits. The first one talks about current max, as you would expect, and the second one talks about this I. And we'll see where this gets used. Do I have well, I also use this in the template condition. That's the condition of the while loop. So that's what is just copied here. To follow the template, remember, we have to do these three things. We have to check that the invariant holds before the loop, that together with the condition of the while loop, it implies that the invariant is reestablished after the loop, and that it gives us the desired post condition at the end. These are these three things that we have to prove. And so Let's go through these one by one. Why does the loop invariant hold at the beginning, before the loop? Well, let's look at the two parts. There's the red and the green part. The red part at this point, the important bit here is that I is 1, because it was just assigned to 1. So current max at this point is just assigned to A0. Now, if I look at the loop invariant and I insert what I is, namely 1, then that's the same as this complicated looking term. But if k is just in the range from 0 to 0, that's really all I'm just saying is it's A0. So that's the red part. The red part of the loop invariant is satisfied at this point, just because it doesn't actually make an interesting statement. It just says current max is A0. Okay? And for the green part, we assume that n is at least 1. So if I turn that around, it means 1 is at least n, and that means I is at most n. Sorry, 1 is at most n, and that means I is at most n, and that's what the loop invariant here says. Okay, so I've proven both parts of the loop invariant of this AND statement are true at position A in the code. And that was the first part of the template that we had to do. All right? The more tricky bit is part 2. That's inside the loop where actually something happens. So I tried to keep this here on the slide. Maybe it's a bit small. So we have an implication that we have to prove. And in this case, we can basically do a direct proof, but we'll use a case distinction. Because in the loop body, there's this if statement, so it makes sense to make a case distinction based on that one. And it's basically the condition of the if, so and I guess I should be precise and say in that specific line, because variables keep changing their values. Now there's two cases that can either be true or false, this if condition. So case A, or let me spell it out. Case A is that is true. So AI is bigger than the current max. That means we have found a new maximum, right? Let me copy it. Okay, so that's all we know so far. But now we have to use the fact that the invariant is true. Remember, we're allowed to use, in this case, we're doing a direct proof. So we assume what's on the left of the implication and try to prove what's on the right. In particular, that means we can use our loop invariant. And from the red part of the loop invariant, we can use this bit. Now, in this case, I has some value that we don't know, so we'll have to leave it symbolic. That's from I, the loop invariant. And now I'm just copying what's on the previous slide. So k between 0 and I minus 1. All right, now we have to use that we know what the if statement will do. Because we're in the true case, we will execute this line 9 and update current max. So in this line, we change the value of current max. Namely, we set it to AI. Right? And that means current max now is AI, but that is nothing but the maximum up to the next position, because we know from this part that the last entry is the largest, so I can go from k between 0 and including I. And I know the maximum will actually be the last element, which is AI. All right. So far so good, but this is not what the invariant says. The invariant should have the I-1 again, so this doesn't seem like we make progress. But then if we look at the next line in code, we are now changing the value of I. And so after that, now I'm sick and tired of writing this all the time. Let me just copy it. Now current max is still the same, but I've updated I. So if I want that to be the same, I have to do the I-1 again, right? I've just taken this term and replaced I by I plus 1. So I have to do the inverse in here. Well, and that is the red part of our invariant down here. That's the red part of the loop invariant reestablished. In this case. We're still in case A. Okay, I'll try to get the indentation right. Case B is the false case, which means I should be able to copy some bits. If it's not greater, then it's less or equal. And current max by the loop invariant still is this. It's almost a bit. It's almost indicating we're doing too much copying. So that's still true because it only uses the loop invariant. But now, because AI is smaller than this maximum in the previous range, I know this is actually the same. So that uses this condition. Maybe I should also do it in blue again. That means that's actually the same than letting k go one further. Now in both cases, we arrived at this statement that current max is the max of the positions up to including I, but for different reasons, right? In one case, we had to do the if and update it. In the other case, we did not update it, but it was still the maximum. And then the rest is the same. So after line 10, we again change I. We update I. So I'll do the same changes here. And so again, the red part of the loop invariant is reestablished at D. Good. So that's almost done, but we also need the green part of the loop invariant. We also have to show that this is still true. And that's maybe not trivial because we change I, right? So to prove this, we use that I really want the code again. I used too much space, so I'll shrink it a bit more. Hope it's still somewhat legible. So at position B, the loop invariant was true, and so the green part of the loop invariant says I is strictly less than n. The only place where we change it is again at line 10. Let me use the assignment. And if I was less than 10, strictly less than 10 before, now if I make it one bigger, it's still less or equal n. And that's what the loop invariant wanted. So also the green part is true. And note that for the green part, we didn't have to do the case distinction. The if doesn't change the outcome there. Now that means we've proven the second part of the statement. And it's a while ago, but we've established this one now. If the loop invariant holds at the beginning of the loop, together with the loop condition, it holds at the end of the loop body. Now what's missing is the last part, namely that we're proving the right thing. And this one will be short, I promise. Can I copy this part? I'd have to take a... I can take screenshots. Let's do it that way. And what we're trying to prove is this. And let's also be lazy and copy the post condition. So that's my service to you. You don't have to remember everything. It's all on the slides. Put it all on the side. So we take our loop invariant and add the condition of the while loop, negate it. That condition was that. So if I take I and negate the condition, what I get is the loop invariant, and the negation of that is I greater equal n. Now if you look at the green part of the invariant, that means I should be less than n and greater, less or equal n and greater equal n, so I is equal to n, right? And now I take the red part of the loop invariant and insert I, the value of I. And so it says current max is the max for k in the whole range. And ta-da, that's what the post condition was. Okay, so that concludes the third part. Or I can tick it off here. We've proven that if you have the loop condition after the loop, plus the negation of the while condition, so that we actually terminate it. Those two things together imply what we wanted, namely current max is the maximum of the entire array. Oof, yeah, I know, it's tedious, right? This is the level of detail that you need for formal verification. That's the level of detail that a computer can follow a proof and check step by step that it's correct. I would have to spell it out in a different language. I've used English language to convince you, and you can formulate it in a logic language for a computer. But that's the kind of level of detail where no further doubt is possible. We'll often stop a little higher level than that with a bit more abstractions in. But I want you to be able to recognize when a proof is formal and at least be able to read them. You'll do another 2 basic examples of that form in the tutorials, namely on mathematical induction and on the termination proof. And hopefully then you have at least a feeling for what these proofs should look like.